Hello, this is Rick from MathX, and this is part 2 of my mini-series in which we explore all the different ways to find the area of a triangle. Today we'll be going over Heron's formula and seeing how we can use Heron's formula to find the area of a triangle. Heron's formula states the area of any triangle is the square root of s times s minus a times s minus b times s minus c, where a of course is the area, S is the semi-perimeter, so half of the total perimeter. A is a side length, B is a side length, and C is a side length. Now, this formula was derived many years ago by this Greek guy named Heron of Alexandria. And this formula, even though it has a little bit of a complicated proof using law of cosines and a lot of computations using law of cosines, it's quite simple to use. We just need to be able to calculate for the perimeter of a triangle, take half of that to get the semi-perimeter, and then just use the remaining side lengths in respect to the semi-perimeter to compute for the area of a triangle. So this can be a very powerful tool in computing for areas of triangles whose side lengths we know. So let's try an example. Right here we see a 13, 14, 15 triangle. And these triangles are very important because in lots of computations you'll see them appear in many different problems. So we can practice using Heron's formula by computing the area of this 13, 14, 15 triangle. So we can start. In this 13, 14, 15 triangle, the first step would be to take its semi-perimeter. If we add all the sides up, we get a perimeter of 42. So half of that would give us a semi-perimeter of 21. Then, by subtracting this 21 from the first side length, 15, which matches our s minus a term, we would get 6. Subtracting it from our second side length, 14, to get our s minus b term, we'll get 7. And subtracting 13 from this 21, we're going to get 8. So if we compute for the square root of 21 times 6 times 7 times 8, we'll get the area of this 13, 14, 15 triangle. However, this is kind of a hard computation, so a good skill to be able to use in conjunction with Heron's formula is prime factorizations. So to minimize the amount of brute force calculation and minimize the chance of error in doing this calculation, we're going to take the prime factorization of these numbers. Doing so, we see that 21 will get prime factored into 3 times 7, 6 will get prime factored into 3 times 2, 7 will just stay the same, and then 8 can be written as 2 cubed. Now if you look at these numbers, we notice that we have a 3 here and a 3 here, a 7 here and a 7 here, and we have a 2 here and a 2 cubed here, but that can be written as 2 squared times 2 squared. So we can take a 2 squared, a 3, and a 7 out of the square root and write it like that. Then computing for the area, we just need to multiply these numbers out. So that would be 4 times 3 times 7, giving us an area of 84. So we've just used Heron's formula to find the area of a 13, 14, 15 triangle. Showing how useful this tool is in finding the area of triangles whose side lengths we already know. However, if you're still not convinced, we can verify that this answer is correct just using the normal method of finding the area of a triangle. The method that I explained in the previous video, just using base times height. And even though we don't have clear height just by looking at this triangle, we're about to exploit a cool property that a 13, 14, 15 triangle has. If we drop an altitude from B to the opposite side AC, we see that that altitude must have a side length of 12. Because then it would break up the opposite side into a segment of 9 and 5. And this 5 and this 9 would add up to 14, making 12 the height. This shows that this 13, 14, 15 triangle is also a combination of two well-known Pythagorean triangles with Pythagorean triplet lengths of 5, 12, and 13, and 9, 12, and 15. So this is the cool property that people often associated with 13, 14, 15 triangles. The ability to break it into two Pythagorean right triangles with well-known Pythagorean triplets. And obviously, if we use this height and we use this base, multiplying it and dividing by 2 will give us 84. So now that we know what Heron's formula is and have a feel on how to apply it to solve for the area of triangles whose sides we know, let's try another practice problem. This problem is the number 16 from the 2011 AMC8, and it states, let A be the area of a triangle with side lengths of 25, 25, and 30, and let B be the area of a triangle with side lengths of 25, 25, and 40. What is the relationship between A and B? So we could draw out all these triangles and then try to toil through finding an altitude because they're both isosceles triangles, so dropping an altitude to the unequal side and then using Pythagorean theorem like that. But it's actually going to be much easier to use Heron's formula in this case and then compare the areas just like that when they're in Heron's formula. So then applying Heron's formula to both of these triangles by finding its semiperimeter and subtracting each of its side lengths from its semiperimeter. Well, first we find that the semiperimeter of this first triangle, A, is 40 because 25 plus 25 plus 30 would give us a total perimeter of 80, and dividing by 2 would get 40. Similarly, a semiperimeter of triangle B would be 45 because if we add up all the side lengths, 25, 25, and 40, we're going to get a sum of 90, and half of that is 45. So plugging this into Heron's formula, for the first triangle, we get that the semiperimeter, 40, minus the semiperimeter minus the first side, 25, would give us 15, minus the second side, which is still 25, would give us 15 again, and then 40 minus 30 would give us 10. So we get that to be the area equation for the first triangle. For the second triangle, we can do pretty much the exact same thing using Heron's formula and write out our Heron's formula equation for the second triangle. Since we've established that the semiperimeter of this triangle is 45, we plug it in at the beginning and then we subtract the remaining side lengths from 45. So 45 minus 25 will give us 20, 45 minus 25 again will give us 20 once again, and then 45 minus 40 will give us 5. So here we have the area equations for each of these triangles. Now, as I've said before, computing this value out and taking the square root just by multiplying everything up will be kind of difficult because we have a lot of numbers here and the numbers aren't really that small. So it would be in our best interest to take the prime factorizations and see what happens. And by doing so, we actually notice something very interesting. If we take the prime factorization of the first one by taking out 3 2's from the beginning, 1 2 from the 10, and 4 5's from the entire thing, and 2 3's from the 15 and the 15, we see that the prime factorization of the area of the first triangle is the square root of 2 to the 4 times 5 to the 4 times 3 squared. And we also notice that if we do the exact same thing with the other equation, take the prime factorization of the numbers inside the square root, it comes out to be the exact same thing because we would take two squares from the 20s and take 1 5 from each of the terms and a 3 squared term from the 45. And the prime factorizations of these two computations are the exact same, meaning that the area of these triangles is also the exact same. So in the end, we didn't even need to calculate our answer. We just need to express it in Heron's formula and take the prime factorizations. And then we got that the areas of these two triangles are the same. So the relationship between the triangle A and B, well, it's A equals B, or C. So in this video, we've gone over Heron's formula, and we solved an AMC practice problem. Along with that, I've also showed you how Heron's formula can be used to prove some cool properties with 13, 14, 15 triangles. So hopefully this gets my point across. Heron's formula is a really powerful tool in finding the area of a triangle. With just all the side lengths, you can find the area of any triangle by applying Heron's formula to said triangle, and it's not that difficult. In this case, we've used it to solve a number 16 on an AMC8. And even though it's possible to solve this number 16 using other methods, by using Heron's formula, we've greatly decreased the number of steps and the number of computations, showing how vital it is to know Heron's formula in order to do any sort of computation math. So this is the second method of finding the area of a triangle. And this one can only be applicable if you have all the side lengths provided to you. But what if you only have a couple of the side lengths and an angle? Well, that's where my next method will come in. And I'll explain in the next video how to find the area of a triangle knowing only two side lengths and the angle between them. So tune in next time if you want to figure out how to find the area of a triangle with only two sides and an angle.